Bom dia a todos, good morning. Hoje nós estamos recebendo professor Michel Gallo from Naples University. He is full professor of Naples Università di Napoli Oriental. He is coordinator of the postgraduate program of his university and also treasurer of the Italian Statistical Society. And today he will present this talk about machine learning and compositional data, integrate constrained optimization in the Aitchison space. So thank you very much, Professor Gallo, to spend your time with us. And
good morning, everyone. I want to before say thanks to Francisco to invite me here in Recife and for your introduction. About my talk, I want just to consider that compositional data, many people know that this kind of data is just closed data. And we want just to consider how we can work with this kind of data in machine learning field. So the outline of my talk is just to consider before to introduction of compositional data and the problem that we have to analyze this kind of data with statistical tools. And after we just consider two kind of regression models just to analyze this data from a traditional approach and a new approach based on the Riemannian manifold. And after we have just some case studies that just for show some results, this research, the approach to analyze this data. So about compositional data. Compositional data just has these characteristics. They are closed data because they just lie on a specific space that its name is simplex. Simplex means here. Okay, here, no. Not enough. Just indicate here is just a space where all elements are strictly positive. In this case, we consider just the real data and not complex, but we can use the same in the complex field. And the sum for each compositional vector is equal to a constant. Here just equal to 1, but we can use more different scale. For example, 100, 1 part per million, 1 million, or other. Every time stay in the simplex. But the very important aspect when we analyze compositional data that they stay on the simplex, but we want just to consider the relative information that are inside our data. And I can explain better with this slide. It's a very small example. Here you can observe that you have that we have three simples. The first, the sum is 203, and second, third is 160. And all the variables, all the elements inside the vector are strictly positive. So in this case, these three vectors, these three symbols just lie on the same positive orthogonal real space. And here we can observe that the point 1 just stay on the positive orthogonal real space, but on this red simplex. When the samples 2 and 3 again stay in the same positive orthogonal real space, but on the blue simplex. And here we can observe that the distance between the sample 1 with the sample 2 or 3 is very, very far. What happens when we want to analyze this kind of analysis with the compositional analysis? We just need to move all data, all our samples on the same simplex, the black one. And what happens? Happens that the sample 1 now is very close to sample 3. So from a geometrical point of view, distance just give information about the variability of our phenomena. So what we have done when we use this operator, the closure operator, we just remove the different magnitude. So we just split our information inside the original data in two parts, the magnitude and the relative information. And the magnitude is a part of information that is very, very important. So just to hide the relative information. So for this reason, when we want to analyze our data in a compositional form, we need to consider that we have just to split it and analyze in two different parts, the magnitude and the relative information. And our focus now is just to consider how we can analyze the relative information inside our dataset. Without that, magnitude just hide this part of information. The problem is this: working simplex is not very simple with the traditional statistical tools. The first that just say that was Pearson in 1897 and Chase in 1960 just observed the problem that we have when we consider the correlation, for example, about our variable, when we work with data that just lie on simplex. So here we have just a small example on about this kind of problem. The example is just to consider some soil samples, 3, and we have two researchers. The first researcher just want to observe it on these soil samples, the animal, vegetable, mineral, and water part. Okay, so this is the matrix of our data. What happens when we use the closure, when we use the correlation with this data? We can observe here for research A that the correlation between animal and vegetable is positive, 0.5. Now, on the same soil samples, a second researcher just dried the soil samples because said, okay, water is not important. Just we want to consider the correlation between animal, vegetable, and mineral. So the data set from the same soil samples now is this. And the correlation that we can observe between animal and vegetable is negative, minus 0.57. So the two researchers with the same statistical tools, with the same data, just give two opposite information. So this is a problem. And to solve this problem in literature, just is used some adequate function. What means adequate function? That has some particular characteristics. The first is scale invariance. If you remember in the first slide, I just say that it's not important when we move in simplex if the sum of all elements is 1, 100, 1 part per million, 1 million, or other, because you want just to consider relative information. So the scale invariance means if we change the scale, the results should not change, must not change. And the second characteristic is the permutation invariance. Means that if we just change the order where we collect the part of our composition, the results should not change. The third characteristic that we have to consider to have a correct compositional analysis is to use a function that is subcompositional coherence, the example that we have seen before. So if we consider a composition or a subcomposition for the same data set, the inference, the results that we have between the same part that we have in subcomposition and full composition should not change. So we search this kind of function. And in literature, this kind of function is used now, is just the regression. Aitchison in 1982-1986 proposed three kind of regression: additive regression, pairwise regression, and centric regression. How we can get centric regression? It's very simple. We have a vector. Each part of this vector is a positive value. We consider just the geometrical means for this vector, and we consider the relation between each part with this geometric means. 2003, Herzog and others proposed another kind of regression, isometric regression transformation, that used just to consider before in logarithm scale the compositional vector, and after multiply with the transpose of matrix V. That is a matrix that has just these characteristics. The sum for all column is equal to 0. And if we consider the pre-multiplication with this transpose, we have just the identity matrix. In literature, there are some other regression, but these two are the most used in literature at the moment. So we consider here just this. Well, we said that the space for the composition is the simplex. And Aitchison proposed some operators with this to work directly in the simplex. The box plus, box minus, and box times just indicate the perturbation, inverse perturbation, and powering operators that we can observe the same on this other side, where we consider in the real space the Hadamard product, the inverse Hadamard product, and the power. So just multiply element by element between the two vectors, or just the ratio between the elements of two vectors, or just we consider the power with the constant alpha. And after we use the closure operator, there is, and from mathematical point of view, just an equivalence between these two operators. But the first one is more, is just used for the simplex. And with these three operators, we can define these other operators. We can consider the Aitchison inner product that are given just by this formula. We can consider the Aitchison norm and the Aitchison distance. So we need just this algebra to work in simplex. Well, say that we can have several types of regression model. In this case, we have that the predictor is just a scalar, and we have the response is a compositional vector. So if we want to use just the notation, the Aitchison algebra, we can write the model in this way. So it's just a simple model that we have with the regression, but use different operators. And because powering just is the product, and the permutation is just the sum in the real space. What happens? That if we want to estimate the parameter of this model, we can do in this way. The intercept, so it's just a vector, because we have more than one, because compositional vector have more variables. And we can just before estimate the mean for the response and for the predictor. Predictor is on a real space, So we can use just the algebra that everyone know. In simplex, we need to use this other operator, but we can calculate the mean without problem. And again, we needed to have the intercepts, we needed to know the slopes. To obtain slopes, we can use just this notation, and we can calculate without a problem the this scalar in the real space and this quantity in the simplex. So Aitchison geometry is sufficient to calculate the exact value in the simplex without problem. Okay, so it's very simple, this model. What about this other model? This model we will call type 2 regression model. Here we have that the compositional predictors, so X are just composition, and Y the response is in a real space. So the model just changed in this way because we need the Aitchison inner product to define the model plus the intercept that is just one because we have just one response variable. And can we estimate the parameter of our model? Yes, of course. We can use again to estimate the mean for response and for predictor. In this case, we just change the operators because we are just change where stay response variable and predictor variables in the two different space. And so we can use the Aitchison inner product when we know the slopes just to get the intercept without problem. The intercept without problem. But what about the slopes? Slopes have a problem because here we can observe that we don't have the inverse of the powering operator. So with the algebra, the Aitchison algebra is not sufficient just to estimate the parameter of the model in this case. So in this case, we can solve this kind of problem with the two different approach. One is just the extrinsic approach. So originally our data say in simplex. And we can use a function, isometric regression or centric regression or some other, just to move data from the original space in a real space. And after, we can use ordinal least square just to estimate the parameter of our model. And of course, the original space is simplex. So we need to come back in simplex with the slopes that we have estimated. So we can use just the inverse of isometric regression and to obtain the parameter inside simplex. And we can do that. This approach is used for both type 1 and type 2 models. So in case we have a multivariate linear regression or multiple linear regression. It's work. Yes, it's work. If you just search in papers for compositional data, you can find at the moment this kind of approach for in all the literature. But what about the idea of Trentafilov, myself, Todorov, Simonacci? Was just to consider that simplex is natively in a Riemannian manifold. So it's not very good just to jump from one space to another space and go back. And we propose just to estimate the slope inside the simplex. How? Just with an algorithm that just to move and obtain the true value just to move on a geodetic path. without move from simplex. Well, was just the original idea, and to do that, we need to consider the characteristic of a manifold, because simplex is a smooth in a manifold space, where it's just a flat p minus 1 dimensional surface. Okay, so they have just this characteristic, the simplex this characteristic. And when we work in manifold, we consider as a very important operator the tangent space. Tangent space is just to consider that if we move in a surface that is just smooth, in each point we can use just Euclidean geometry just to calculate just the direction where the objective function can be minimized. And after that, we decide the decision started from one point. We just search the point, we move with our algorithm in that direction with the end step. And after we remain just to constrain that the slope that we are looking for, we are search, just to stay in simplex. And we repeat this operation many, many times. What is very important, that the value that we won't just estimate should have always to respect this constraint. So the sum is equal to 0. So if there are some slopes that go up, there are some other that go down, because the sum should be 0. And of course, the simplex is just a flat, and in each point we can consider as a Euclidean point. So we can just start from any point, there is no problem. But what happens in Aitchison, in manifold? That we need just to decide the mean, and we need to decide the distance. And distance we can use between two compositions, B1 and B2. We can use just the Frobenius norm just to calculate this distance. And if we consider that in simplex we have n different compositional vector, we need to minimize just this function, where V is just the Riemannian mean that we search just to minimize the square of the Frobenius norm between this vector. So after some algebra, we can observe that the minimum of this function is just this. And we can minimize this objective function just to consider the Euclidean gradient that here we can observe. And in every step, we just have to move the vector that we find just to stay on simplex. So to respect the constraint that the sum of all elements is equal to 0. So we do just that. And it's possible to show that this algorithm converge to the optimum of the solution without mapping, so without jumping from a simplex to real space and back. So now we have to consider the algorithm that we propose is just interior point flow for type 1 regression model. We need to minimize this function, where delta, a residual part, is just given by this formula. And the solution, the Riemannian solution, is just given here. We need to use the Euclidean gradient inside. This is the formula complete that we used. And with this kind of this type of regression model, we don't have a problem. Here we have just the algorithm that is just split in 3 parts. The first, just we need to calculate the means for predictor and the predictor and the response variable, and we remove because in simplex we want just to before calculate the slopes, okay? So we just remove the mean for the 2 variables, the 2 kind of variables, and after we use just the interior point flow integration, just to use the OD function that stay in the solved package in R. It's just ordinary differential equation, and step by step, it's just integrate all, and we can obtain the slopes, and we assure that sum is equal to 0 by the constraint operator. And after, in the third phase, we just calculate intercepts, the estimation of our response variable, and the residual if we want, we need the inference on these parameters. About the other model, type 2 model. Okay, the model is different. We have the Aitchison inner product inside. So we can use just this characteristic. The Aitchison inner product can be written in this way. We have 2 vectors, and we use just the central logration or the isometric logration transformation on the original data, just to calculate the residual part. And after, we use just the interior point flow algorithm to estimate our parameters, our slopes. The algorithm just works in this way. So in phase 1, we remove the mean for both set of variables, just because we don't want the intercept inside the OD algorithm, and we use it just to initialize by an uniform distribution, and we just estimate before residual. After we use the gradient, we remove the gradient. We just consider the gradient inside the simplex, and after we accumulate in this way, and we just stop the algorithm when the value doesn't change, of the slopes doesn't change the slope, because the epsilon is just met, so it's enough adequate for the value that we have fixed. And after, we use the closure operator just to have the slopes with the sum is equal to 0. And finally, we obtain the intercept and the estimation of our response variable. So this is about the algorithm, the intrinsic approach to solve the regression models in simplex. Here, we have to consider in the papers that Trentafilov, myself, and Todorov and Simonacci just submitted to statistical papers, just we have used 4 datasets. The first is Articlic dataset. The second is a GEMAS dataset that I don't show here for the type 1. For type 2, there is the Coxit dataset. And we consider here just the probiotics intervention dataset. All the routine and the dataset you can find on a repository that the address is here. And what about the analysis? Before, this is very traditional dataset for compositional analysis. It was given by Aitchison 1986 and used 39 sediment samples and observe 3 parts, sand, silt, and clay, that was collected in a different depth, and to analyze in the depth, how the depth in logarithm scale just influence the parts of the different in different samples. And here we have the result for extrinsic approach, and with the IPF algorithm, so intrinsic approach. You can observe that data set, the results are just the same. So there is not a difference between them. But here we can observe that the set is a toy data set, very simple, because in real world, the problem is more complicated. In this other data set, we have to consider 44 samples. And with these 44 samples are just used to profiling 389 human blood serum lipids and 130 intestinal genus level bacteria. And we want just to observe just the genus level bacteria inside these 44 samples, where 22 was just used the treatment, and the other was just placebo. And what happens? Here we can use just the intrinsic approach, because we have that the number of variables is higher than the number of the samples. So we cannot use ordinal least square to estimate the parameters. Here we can observe, we can use it, and we can estimate without problem. And in real world, there are many problems as this kind. For example, if we consider genome or other problem, we have a lot of variables. In machine learning, generally, we have data set. And ordinal least square requires that no singularity of covariance metrics. Many times on real data we have. With this approach, we can just solve this kind of problem. Again, we need to consider, and here we have just the conclusion of my talk, that when we work in simplex, we use the log regression function. So when we stay very close to here. Just the first. When we stay very close to the edge, so what happens? That for one part, the value is very high, and for all the other, they are very low. And when we use the logarithm, these other parts, or when we have a large number of parts inside our compositional vector, there are that many parts are very close to zero. So in logarithm scale, it's just go to minus infinity. And this is a problem. Because if we use the ordinal least square, we can observe that maybe that we can have some problem to estimate the parameters. We have problem with the outliers, for example, and other. This problem is just solved with the Riemannian approach, because it's just an algorithm. So when just we go closer to the edge, so we have that the dependence, just the grade is just go down quickly. We just, the algorithm just reduce the step. The step is smaller. So just to converge, just is slower in this part of the algorithm, and to converge to the optimal value. Problem that we have when we use a traditional ordinal least square. And so I can conclude here just to consider some reference that the main stone for the compositional analysis is just the book of Aitchison, 1986. And for the manifold, the book that Trent Filov and myself wrote in 2021, and this is just the paper that we have submitted to statistical paper about this approach. Okay, thank you for your attention.
Well, thank you very much for this nice presentation. Someone would like to make a comment or observation or have a question? I have a question because, well, I got the general idea, but in the beginning, when you presented the Aitchison approach, so it was just regarding univariated regression. When you have only x in function of y in function of x. So yeah, so there is not an explicit cost function here. What is in this case the cost function to minimize? There is not explicit now for this this part.
For this part, for the Riemannian approach, we just are working on a simulation data set. But we have said in this data set and the several others that we have just tried, the compositional cost is very, very low because it just converges very quickly. I don't write in the algorithm here the epsilon, how we decide, okay? So if we decide an epsilon that is very, very low, okay? So -8 and other. So generally after 3-4 steps, just converge to results. The time, the computer time was 0.06 seconds for the big data set. So from a computational point of view, we don't have a problem. The problem that we have, for example, with the real data set, not just toy data set, is the determination index. Sometimes if we fix this very low, we can have some negative R-square. But we observe that when we just increase this, so the time doesn't increase, but it just get a positive, a very close to the traditional algorithm when we compare with the toy data set. Because with the real data set, the traditional approach doesn't work. You don't find a very interesting application of the traditional Aitchison approach in literature.
Okay. And in this algorithm, these steps, they come from the optimization of the objective function?
Yeah, we use just
so
ordinary differential equation. Just it's a very low function in R, so in Manot for MATLAB, just to estimate. It's just tradition. The original idea is every time just to leave the slopes, the parameter inside the simplex, just to move along a geodetic path. This is
the algorithm point interior.
Yes, you just every step we just before estimate the direction, and after we put on simplex. If we have a very long step, we can go outside of the simplex, so in a positive or tangential space. So this is the problem that can have with the traditional approach. For this reason, the traditional approach, I find I work with compositional data from time, more than 20 years. And every time when we use the regression model, we just observe that, okay, but it's just a toy data set. There's no real problem.
But now,
So here we can observe that when we have a simple data set, it's give the same result. And the time that required are just the same, because in any case, here we need just to jumping 2 times from the 2 space. So it's deterministic, okay, but we use ordinal least square. So inside there is always calculated, and after we need to cover back every time. So for this reason, for me, it's very interesting research for this topic that can be used in many different fields too, not only for composition, but in many other.
okay. Thank you very much. Any comments or questions? Okay, thank you very much again for your nice presentation. Thank you very much to spend your time with us.
Thank you, Francisco. Thank you to all people that stay here.